We continue our study of vectors by looking at surfaces in space. So we start by looking at lines in space. Now recall that to write the equation of a line in the plane, we need to know either 2 points that it passed through, or a single point that passes through, plus its direction. In the plane, that's the slope. So in space, we describe the direction of a line using a vector that's parallel to the line. Recall that two parallel vectors will have either the same direction or opposite directions. Also recall that the scalar multiple of a vector will either be in the same direction or the opposite direction, depending on the sign of the scalar. So this gives us our lemma. Two vectors u and v are parallel if and only if there is some scalar k such that u is equal to kv. Now let L be a line in space passing through the point x0, y0, z0. Let v equal ABC be a vector that is parallel to L. Then for any point q equals x, y, z on the line, we know that the vector pq is parallel to the vector v. Thus there must be some scalar, called t, such that the vector pq is equal to t times v. So pq is equal to tv. Now pq would be x minus x0, y minus y0, z minus z0. We can split this up into xy minus x0, y0, z0. Then we can pull in the t. We have equals ta, tb, tc. We can then solve for x, y, z. And that is not y0, z0 plus ta, tp, tb, tc. Then using vector addition, that becomes x0 ta, y0 plus tb, and z0 plus tc. So equating components, we get x is equal to x0 plus ta, y is equal to y0 plus tb, z is equal to z0 plus tc. If a, b, and c are not all 0, then we can solve these three equations, each for t, and set them equal to each other, which will give x minus x0 over a is equal to y minus y0 over b is equal to z minus z0 over c. So that first set of equations, x equals x0 plus ta, y equals y0 plus tb, z equals z0 plus tc, are called the parametric equations of the line. The other equation, the x minus x0 over a equals y minus y0 over b equals z minus z0 over c, is called the symmetric equation of the line. So let's go ahead and find parametric and symmetric equations of the line that passes through the points 1, 4, -2, and -3, 5, 0. So we first need a parallel vector. Well, if we say that's point P, that's point Q, a parallel vector would be the directed line segment P to Q. So we get -3 minus 1, 5 minus 4, 0 minus -2. There's our parallel vector. We may now choose either point P or point Q. I'm just going to use point P. We can get x is equal to 1 minus 4t. Y is equal to 4 plus t, and z is equal to negative 2 plus 2t. So here are our parametric equations. Now, notice our vector does not have a single zero in it, so we can also find the symmetric equation, which would be x minus 1 over negative 4 is equal to y minus 4 over 1 is equal to z plus 2 over 2. Let's now look at the distance between a line and a point. So let L be any line in the plane, let M any point not on the line. We define the distance from M to L as the length of the line segment MP, where P is a point on L, such that MP is perpendicular to L, as we see over here. If instead we are in space, the distance is still defined the same way. However, in space, there's no clear way to know which point on the line creates such a perpendicular line segment. So, we select an arbitrary point on the line and use properties of vectors to calculate the distance. Let P be an arbitrary point on the line L, and let V be a direction vector for L. Right, so here's our line L. We choose an arbitrary point P, and V is a direction vector. Now, the vectors PM and V form adjacent sides of a parallelogram. And as we saw, that's going to have the area magnitude of PM cross V. But the area of a parallelogram is simply base times height. That is, that magnitude of PM cross V is the magnitude of V times D. And D is our value in question. It represents the distance from the point to the line. All we have to do is solve for D, and we have our formula. So the distance from a point to a line is the magnitude of PM cross V over the magnitude of V, where P is any point on the line, M is the point in question, and V is a direction vector for the line. So we now wish to find the distance between the point 113 and the line given by the symmetric equation x minus 3 over 4 is equal to y plus 1 over 2 is equal to z minus 3. So we need a point P on the line and a direction vector for the line. Well, the point P is easy enough. We can use 3 minus 1, 3. And the direction vector is also easy enough. It's 4, 2, and 1. Right? Because remember, this is over 1. So, our vector PM would be -2, 2, 0. Let's go ahead and now calculate the cross product of PM and V. All right? So we get 2 times 1 minus 0. Then we get -2 times 1 minus 0, and we take the negative of that. Then we get -2 times 2 minus 2 times 4. So -4 minus 8, -12. And let's go ahead and factor out 2. Which means that the magnitude of PM cross V is 2 times the square root of 1 plus 1 plus 36, which is 38. So the distance is 2 square root of 38 over the magnitude of V, which is the square root of 16 plus 4 plus 1, so square root 21. You could also write this as 2 times the square root of 38 over 21. Now, given 2 lines in the plane, we know that they are either equal, parallel but not equal, or they intersect at a single point. In space, we have a fourth possibility. They are not parallel, and they do not intersect. Such lines are called skew. To classify lines, we need to know 2 things: whether the direction vectors are parallel, and whether the lines share a point. This graphic summarizes the 4 possibilities. So if the direction vectors are parallel and the lines share a common point, the 2 lines are the same line. If the direction vectors are parallel, but they do not share a common point, then the 2 lines are parallel, but not equal. If the direction vectors are not parallel, but they do share a common point, then the lines will intersect. Specifically, they'll intersect at the common point. And if the direction vectors are not parallel, and the lines do not share a common point, then the lines are skew. They are neither parallel nor do they intersect. So for each pair of lines, we will determine their relation. So we start off with these 2 lines. Well, line 1 has the direction vector 2, 1, 1. Line 2 has the direction vector 1, 3, -2. Well, notice that these vectors are not parallel. Now we need to determine if they have a common point. So set the x's equal to each other, the y's equal to each other, and the z's equal to each other. So we have 2s minus 1 is equal to t minus 3. S minus 1 is equal to 3t plus 8. And s minus 4 is equal to 5 minus 2t. Let's take a look at this first equation. And this says that t is equal to 2s plus 2. So let's now plug this t into this second equation. So that'll give us that s minus 1 is equal to 3 times 2s plus 2 plus 8. So s minus 1 is equal to 6s plus 14. So negative 5s is equal to 15, which means that s is equal to negative 3, and that t would have to equal negative 4. What we now do is we take these two values and we plug them into the third equation. So we'll get negative 3 minus 4 is equal to 5 minus 2 times negative 4. We wind up with negative 7 equals 13. Wait a minute, no it doesn't. This is what we call a contradiction. This means that there is no common point. So the lines are skew. So now what about these two lines? So again, we're going to need direction vectors. So the first direction vector is 1, negative 1, 1. The second direction vector is 2, 1, 1. Well, they're not parallel. So what we need to do now is we need to determine if they have a common point. To do this, we need to put them into parametric equations. So the first line has a point 0, 0, 0. The second line has the point 3, 0, 2. So we can describe the first line by the equations x equals s, y equals negative s, and z is equal to s. The second line can be described, x is 2t plus 3, y is t, and z is t plus 2. So as before, x equals x, y equals y, z equals z. So let's take this second equation rather, and plug it into the first equation. So we have s is equal to negative 2s plus 3, which means that 3s is 3, And so s is equal to 1, which means t has to be equal to negative 1. Take these two values, and plug them in to that third and final equation. So we get 1 is equal to negative 1 plus 2, so 1 is equal to 1. That checks out. This means that these two lines intersect at their common point, which is where s is 1 and t is negative 1. So plugging s equals 1 back into line 1, we get the point 1 minus 1, 1. What about these two lines? So again, we're going to need direction vectors. So v1, the first direction vector, 6, negative 2, 3. The second direction vector is 6, negative 2, 3. Oh, these two vectors are equal, which means that they're parallel. We need to describe the second line. Well, the second line can be described by x is equal to 4 plus 6t, y is equal to negative 3 minus 2t, z is equal to 1 plus 3t. So x equals x, y equals y, z equals z. That third equation implies that s is equal to t. If we now take that and plug it into this second equation, notice that we get an immediate contradiction. We have negative 2t is equal to negative 3 minus 2t. That's nonsense. So they do not share a common point. Therefore, the lines are just parallel. Let's now turn our study to planes. So there are several ways to characterize a plane. First is given any 3 points that do not all lie on the same plane, on the same line. There is a unique plane that passes through these points. Given 2 distinct intersecting lines, there is exactly one plane containing both lines. A plane is determined by a line on any point. A line and any point that does not lie on the line. And finally, imagine a pair of orthogonal vectors that share an initial point. As you twist one of the orthogonal vectors, the other spins around and sweeps out a plane. Now let's try and describe the plane mathematically. So let n equal ABC be a vector. Let P equal x naught, y naught, z naught be a point. Then the set of all points PQ, the set of all points Q equals x, y, z, such that the vector PQ is orthogonal to the vector n, forms a plane. We call n a normal vector to the plane. This just simply is another way of saying that it's orthogonal. It's perpendicular. So when we talk about lines, we use perpendicular. When we talk about two vectors, we use orthogonal. When we talk about a vector and a plane, we use normal. Now, since the vector PQ is orthogonal to the vector n, we know that their dot product must be 0. So that is ABC dotted with x minus x naught, y minus y naught, z minus z naught must equal 0. So doing the dot product, we get A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to 0. And that is summarized in this definition. So the equation n dot pq equals 0 is called the vector equation of the plane. The scalar equation of the plane would be the A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. Now we can then expand this out and express it as the general equation of the plane, which is ax plus by plus cz is equal to, plus d is equal to 0, or ax plus by plus cz is equal to negative d, where d is negative ax naught minus by naught minus cz naught. So we're going to write an equation for the plane containing the points 1, 1, negative 2, 0, 2, 1, and negative 1, negative 1, 0 in both standard and general forms. So we need to find a normal vector. Well, remember that the cross product of two vectors gives you a vector that is orthogonal to both of them. So why don't we find two vectors contained in this plane? Well, two such vectors would be the vector PQ and the vector PR. So PQ would be negative 1, 1, 3. PR would be negative 2, negative 2, 2. And of course we can factor out that 2. So our normal vector would be their cross product. And remember, if I use properties of cross products, I can just multiply the cross product of minus 1, 1, 3, minus 1, minus 1, 1 by 2. So we get 2 times 2 minus 1 and 1. I'm sorry. 4 minus 2 and 2. Factor out another 2 and we have 4, 2 minus 1, 1. Now the only difference between 2 minus 1, 1 and 4 times that is the magnitude. In other words, if I take away that 4, right, if we just drop out this 4, we still have a normal vector. And so that's what I'm going to do. I'm going to take my normal vector to be the vector 2, minus 1, and 1. So the standard equation would then be 2 times x, and I have to pick any point. Let's pick P, x minus 1, minus 1 times y minus 1, plus 1 times z minus negative 2 is equal to 0. And here is our standard equation for this plane. For the general equation, we would have 2x minus y plus z, now plus d. Remember, d is negative 2 times x naught, so we're going to have negative 2 plus 1 plus 2. That's just plus 1. So you can have 2x minus y plus z plus 1 equals 0, or you can also have 2x minus y plus z is equal to minus 1. Either of these equations would satisfy the general equation. Let's now find an equation of the plane that passes through the point 1, 4, 3 and contains the line given by x equals y minus 1 over 2 equals z plus 1. So we have 2 points. We're going to call this point Q. So point P will be any point on this line. So 0, 1, minus 1. We need 2 vectors. Well, one vector would be the direction vector for the line. Right, so that vector is 1, 2, 1. Our second vector would be this, the vector PQ. And that is the vector 1, 3, 4. This will allow us to find the normal vector. And so we get as a normal vector 5, minus 3, and 1. So the equation would be 5 times x minus 1 minus 3 times y minus 4 plus z minus 3 is equal to 0. And it didn't specify whether it wanted a standard or a general. So let's go ahead and just keep it in standard form. Let's now look at distance between a plane and a point. So this distance is defined as the shortest possible distance from the point to a point on the plane. We find the distance by calculating the length of a line segment that is perpendicular to the plane. So we let R be a point in the plane such that the directed line segment RP is normal to the plane. And we let Q be any arbitrary point in the plane. Well, then, the projection of the directed line segment QP onto the normal vector describes the vector RP. Which means that the distance, which is the length of P, can be described by the vector QP. So the distance would be the norm of the projection of N. The projection of QP onto N, where N is the normal vector. Right? N would be this RP. So we wish to find the distance between the point 312 and the plane given by x minus 2y plus z is equal to 5. Right, well, we have our point. We have a plane. Well, we need a normal vector to the plane. So it would be 1, negative 2. We now need a point Q in the plane. Well, let's set x and y equal to 0. That would mean that y and z equal to 0. That would mean that x has to be 5. So we can take the point 5, 0, 0. Then the line segment Q to P would be negative 2, negative 1, positive 1, 2. So the distance is the norm of the projection of QP onto N, which, remember, was the absolute value of QP dotted with N all over the norm of n. So we get the absolute value of negative 2, negative 2 minus 2 plus 2, which is just negative 2, all over the square root of 1 plus 4 plus 1. So we get 2 over root 6 as our distance. So there are two possible relationships between planes. They are either parallel or they intersect. When two planes are parallel, their normal vectors are parallel. When two planes intersect, the intersection is a line. So let's determine whether the planes given by x plus y plus z equals 0 and 2x minus y plus z equals 0 are parallel, or if they intersect. And if they do intersect, we wish to find the line of intersection. So to determine whether they are parallel or not, we look at the normal vectors. So the normal vector of the first plane is 1, 1, 1. The normal vector of the second plane is 2 minus 1, 1. Well, these are not parallel. So there's no way these planes are parallel, so they must intersect. We now must determine their line of intersection. So set them up. And we now wish to solve this system. So we can use method of elimination here. So if we just add the two together, notice that we're going to cross out the y. We're left with 3x plus 2z is 0. This means that x is equal to negative 2/3 z. If we now plug this back into the first equation, we'll get negative 2/3 z plus y plus z, which is 1/3 z plus y has to equal 0, which means that y is negative 1/3 z. Z can be any real number. So let's set it to be negative 3t, where t is a real number. Then our line of intersection is the line x equals 2t, y equals t, z equals negative 3t. If two planes intersect, then they're going to form an angle. The angle can be determined by the angle formed between the normal vectors. And so we get that the angle theta between two planes is given by the formula cosine of theta is equal to the absolute value of n1 dotted with n2 over the norm of n1 times the norm of n2. And this is illustrated in this figure. So we're going to find the angle between the given pair of planes and use this angle to determine whether the planes are parallel. So our first normal vector, 1, 2, minus 1. Second normal vector is 2, 4, minus 2. So cosine of theta, by the way, we can tell that these are parallel. Cosine of theta, n1 dot n2 over norm of n1 times the norm of n2. So we're going to have the absolute value of 2 plus 8 plus 2, which is 12, over the square root, 1 plus 4 plus 1 times the square root, 4 plus 16 plus 4. So we have 12 over the square root of 144, and this, of course, is equal to 1. So the cosine of theta is 1, which means that theta is 0. Since there is no angle between them, the planes are parallel, which, of course, we can easily tell by looking at the normal vectors. So what about these two planes? So again, we need the normal vectors. So first normal vector would be 2, negative 3, 2. The second normal vector would be 6, 2, negative 3. So cosine of theta is the absolute value, 12 minus 6 minus 6 over the square root, 4 plus 9 plus 4, which should be the square root of 17, times the square root of 36 plus 4 plus 9, but this equals 0. This means that theta is pi over 2. So these two planes are actually perpendicular. And so the planes are not parallel. And finally, what about these two planes? Again, the first normal vector is 1, 1, 1. The second normal vector is 1, negative 3, 5. So cosine theta would be the absolute value of 1 minus 3 plus 5 over the square root of 3 times the 1 plus 9 plus 5. I'm sorry, plus 25. So we get 3 over the square root of 75. I'm sorry, not 75. I was thinking that was 25. Square root of 105. So theta is the arc cosine of 3 over the square root of 105, which means these planes are also not parallel. Now, if two planes are parallel, then we can calculate the distance between them. To do so, we simply choose any point in one of the planes. Then the distance between these two planes is the distance from this chosen point to the other plane. That is, the distance is the vector qp dotted with n over the norm of n, where q is a point on the plane and p is a point not on the plane, and n is the normal vector that passes through q. Now, we can only calculate distance between parallel planes because this distance is constant. If the two planes are not parallel, that means they intersect. Well, that means that the distance between the planes will be changing. It varies depending on the points you choose, the points chosen. Well, let's try and simplify this. So consider the distance from the point x naught, y naught, z naught to the plane ax plus by plus cz plus k is equal to 0. So we let x1, y1, z1 be any in the plane. So then what we get is we have the absolute, d is the absolute value of a times x naught minus x1 plus b times y naught minus y1 plus c times z naught minus z1 all over the square root of a squared plus b squared plus c squared. We'll simplify this. Well, this is almost the standard equation of a plane, right? It just doesn't equal 0. It's the left-hand side. Well, we can write that in general form as the absolute value of ax naught plus by naught plus cz naught plus k, where k is negative ax1 minus by1 minus cz1, and all that over the square root of a squared plus b squared plus c squared. Let me go ahead and write down what k is. Right, so k would be negative ax1 minus by1 minus cz1. And so this is the distance between planes. So let's find the distance between the parallel planes given by 2x plus y minus z equals 2, and 2x plus y minus z is equal to 8. Well, let's rewrite these. So we're going to say plane 1 will be 2x plus y minus z minus 2 is equal to 0. Plane 2 will be 2x plus y minus z minus 8 is equal to 0. So let's pick a point from the first plane. Well, if we set y and z equal to 0, then x has to be 1. So the point would be 1, 0, 0. And this lies in the first plane, right? So this point is from this first plane. So the distance is the absolute value of 2 times 1 plus 1 times 0 minus 1 times 0 plus negative 8 all over the square root of 4 plus 1 plus 1. Right? Remember, since we got the point from the first plane, we get the A, the B, the C, and the K from the second plane. So this is equal to 6 over the square root of 6, which is just simply the square root of 6. So the distance between these two parallel planes is the square root of 6. Let's now move on to looking at cylinders. So a set of lines parallel to a given line passing through a given curve is known as a cylindrical surface, or a cylinder. The parallel lines called the rollings of the cylinder. Now, when most people think of a cylinder, they think of what's known as a circular right cylinder, right? A cylinder whose curve is a circle. However, any curve can form a cylinder. So a circular right cylinder is something like this. I think that's a bad drawing. It's better. Right, so this is a circular right cylinder. Well, this is a standard example, right? So here's a circular right cylinder. So cylinder x squared plus z squared is equal to 25. So when you hear cylinder, this is the type of cylinder that pops into mind. Well, here's a cylinder. This is the cylinder z equals 2x squared minus y. Now, this is definitely counterintuitive. You wouldn't look at this and think it's a cylinder. But in fact, it is. It fits the definition. Here's another one. Y equals sine of x. Well, that's as far into cylinders as I want to get. I'm more interested in the more interesting surfaces. These are called quadric surfaces. So quadric surfaces are the graphs of equations that can be expressed in the form of this general 3-variable second degree polynomial, where each of the coefficients are real numbers. Now, there are a total of 17 quadric surfaces that can be derived from this general equation. We are going to study in depth 6 of them, and the next several slides are going to summarize these 6. So first up is an ellipsoid. So the ellipsoid has the general equation, the general form, x squared over a squared plus y squared over b squared plus z squared over c is equal to 1. Now, if a, b, and c are all the same, then this is a sphere. Now, the ellipsoid can either have its longest along the z-axis, its longest along the x-axis, or its longest along the y-axis. That is totally dependent on the value A, B, and C. Think back to the ellipse you studied in Calc 2. Right, so if C is the largest, then it's going to be along the Z. If B is the largest, it'll be along the Y. And if A is the largest, it'll be along the X. Next, we have a hyperboloid of one sheet. It has the general form, x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. So notice for this surface, two of the variables have positive coefficients and one negative coefficient. So the axis of the surface corresponds to the variable to the negative, right? So we can see here that it's the z-axis that passes through the hyperboloid. Or more specifically, the hyperboloid is opening up along the z-axis. Well, if it was x that was negative, the opening up would be along the x-axis. If it was the y that was negative, the opening would be along the y-axis. Then we have hyperboloid of two sheets, which has the general form z squared over c squared minus x squared over a squared minus y squared over b squared is equal to 1. Now, for this surface, two of the variables are negative and one is positive. The axis of this hyperboloid is the variable that is positive. So again, you can see it's opening up along the z-axis here because the z is positive. If it was the x that was positive, it would open along the x. If the y was positive, it would open along the y. Fourth is the elliptic cone, which has form x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 0. Again, notice that you have two positive variables and one negative. The axis is the axis that corresponds to the negative variable. Fifth, we have the elliptic paraboloid, which has form z equals x squared over a squared plus y squared over b squared. Notice for this surface, one of the variables is linear, which means it has power 1, and the other two are power 2. So the axis of the surface corresponds to the variable that is linear. And finally, we have the hyperbolic paraboloid, which has form z equals x squared over a squared minus y squared over b squared. So the axis of this, again, corresponds to the linear variable. And if you notice, it kind of almost looks like a saddle, right? So the saddle covers the axis of the positive quadratic variable, in this case, the x-axis. So those are the 6 quadric surfaces that we will study. I know this is a long video, however, we just have 2 more examples and then we're done. So we're going to identify the quadric surface represented by the given equations. So first up we have this one. Well, the first thing we want to do is we want to set it equal to 1. So let's divide the entire thing by 144. So we'll have 16x squared over 144 plus 9y squared over 144 plus 16z squared over 144 is now equal to 1. Well, 16 over 144 is 1 over 9. So we have x squared over 9 plus y squared over 16 plus z squared over 9 is equal to 1. So this is an ellipsoid. And it's centered at the origin 0, 0, 0. Yeah, that one was pretty straightforward. Now for the last one. Let's take a look at this one. Well, it's already equal to 0, so we're good. So why don't we group all of our x's together, all of our y's together, all of our z's together. So we're going to have 9x squared minus 18x plus 4y squared plus 16y. And why don't I move, since z only has a linear component, let's move z and the constant over to the other side. So we have 36z minus 25. Well, look, in this first one we can factor out a 9. So we have x squared minus 2x. From the second group we can factor out a 4. So we'd have y squared plus 4y. Now we want to complete the square. Right? So this will lead us to 9 times x squared minus 2x. Now remember, to complete the square, we take half of this coefficient and square it. So it's going to be plus 1, and then we have to throw in a minus 1. Then we have plus 4 times y squared plus 4y plus 4 minus 4, and this is equal to 36z minus 25. So we have 9 times x minus 1 quantity squared, that was the whole point of completing the square, plus 4 times y plus 2 quantity squared equals 36z minus 25. But now we have this 9 times negative 1, so we have to add 9 to that side. And we also have this 4 times negative 4, so we add 16 to that side. So this winds up just giving you 36z. If we now divide everything by 36, we get z is equal to 9 times x minus 1 squared over 36 plus 4 times y plus 2 squared over 36, which gives us the equation z is equal to x minus 1 squared over 4 plus y plus 2 squared over 9. So this is an elliptic paraboloid. With a z-axis. And it is centered at 1, negative 2, 0. That concludes our look at surfaces in space.